morning, everyone. I have your exam posted. It's due this Sunday. No extensions, please. I need to grade both your second homework and your exam during spring break. That's my spring break. Okay. And also, as you would have seen in the exam question, I will not answer any clarifications for the exam questions, just to be fair to everybody. So try your best. I think more of the tools that you have are present in the lecture notes. We've looked at problems that are fairly similar in construct to these exam problems as well. So I hope it's not too much of a sweat. Okay, there might be parts where there might be some issues, but for the most part, I think they're reasonable problems. When you're using any kind of a method to calculate the equation of motion, you want to use a Newtonian technique for these problems because we've not gone through the Lagrange multipliers. Okay, and I will hopefully go through them on Thursday with an example problem. And then I think if we are done with it on Thursday, feel free to use it if you're comfortable with it. Okay. All right, so I want to start off from what we were doing last time. I think we were looking at the stability of the bead on a spinning hoop. So very briefly set up the problem. Okay, here was the bead. ER, E theta, E phi direction, right, and XYZ coordinate system and so on. This is the angle phi. This entire envelope is spinning at a rate of omega about the EZ direction. And I had pointed out when we derived the equation of motion as the double dot is sine theta d by r plus omega square cosine theta. Okay, so this was the equation of motion. And I had pointed out that if this was the angle theta, then in the position that is seen in this particular figure, if I look at the component of the force of gravity, as gravity is acting vertically down, and so I can split it into two components, one along the E theta and then along the ER, and the component along E theta is going to be the following. So this is mg times sine theta. This was the force mg itself. And then we also had a component of the centrifugal force, okay, along the E theta direction. So the centrifugal force is pointing away from the center, okay. And this we split into a component along ER and E theta. And that ended up being mg, and that was omega square sine theta cos theta r omega square. Okay, so these were the components that we had seen. At this point in time, they are both in the same direction, and so at some other point in time when the bead is sitting below here, then the components will be in different directions, and then we will see what happens there. Okay? So we said that we want to study the stability of the system about some equilibrium points, and to do that we wrote this down in the state space system. So theta 1 dot is theta 2, theta 2 dot is sine theta 1, g by r omega square cosine theta 1, and then we decided to find the equilibrium points, or the fixed points. stability analysis, and we did that by saying that at an equilibrium point, theta dot and theta double dot are both 0. So this is a point where the particle is completely at rest. And if I do that, I'll end up with a family of equilibrium points. So this is for all omega square, theta 1 star is plus or minus n pi. Okay, this was obtained by setting sin theta 1 is equal to 0. And then for omega square greater than or equal to g by r, and that should be capital R, sorry, capital R, g by r, then here I have theta 1 star is plus or minus cosine inverse of minus g by r omega square. So this is all stuff from the last class. These are the equilibrium points, a family of equilibrium points, and at all these omega values, theta 2 star is always 0 for us. So theta 2 star is 0, and likewise here, theta 2 star is also 0. Are there any questions until this particular point? This hopefully is not new to most of you, and if it is, now you know it. And what was our aim? Our aim was to say that, okay, if I'm sitting at an equilibrium point, and if I'm giving a small perturbation about the equilibrium point, is the bead going to sit there stably, or is it going to move away and never come back? That's what we're trying to understand. We're trying to understand the stability of these equilibrium points. And we did that. We started doing it by first of all setting up the linearized system. Okay, so we linearized it about theta 1 star and theta 2 star by taking the Taylor series expansion. And in doing so, we ended up with the following set of equations: epsilon 1 dot, epsilon 2 dot is equal to this big coefficient matrix, which is called the Jacobian matrix. So this is df1 by d theta 1, df1 d theta 2. Evaluated at the equilibrium point, multiplied by the column vector epsilon 1, epsilon 2. Where epsilon 1 is theta 1 minus theta 1 star. So epsilon 1 is theta 1 minus theta 1 star. Epsilon 2 is theta 2 minus theta 2 star. So these are the perturbations. F1 and F2, this is essentially F1 for us, and this creature hopefully all of you can see. Okay, this is F2, theta 1. Okay, and our idea was the following. Now this is a linearized system, which means that the solution for epsilon 1 and epsilon 2 can be obtained by calculating the eigenvalues of this coefficient matrix. So the solution is epsilon 1, epsilon 2. This is equal to constant e to the power lambda 1 t, some column vector lambda 2 t, some other column vector. Okay, so this is the solution for the perturbed system, which is obtained by linearizing about a family of fixed points, whatever we choose. And our hope was the following. For a given choice of a set of equilibrium points, let's say that I select theta 1 is equal to 0 times pi and theta 2 star is equal to 0. So for that particular choice, I want to calculate and see what these eigenvalues are, lambda 1 and lambda 2 from the coefficient matrix. If those eigenvalues have a positive real part, the system is unstable. If they have a negative real part, or if they are imaginary, the system is asymptotically stable if they have a negative real part, and if they are imaginary, it is uniformly stable. It just keeps oscillating within a bounded region. So here lambda 1 and lambda 2, these are the eigenvalues of the Jacobian matrix J about a chosen theta 1 star and theta 2.
Yes. So I know for, at least if I recall correctly, the Lagrange multipliers also use lambda, and obviously they're not eigenvalues. Will we be using lambda as well, or?
Yeah, you're right. So they're different. The Lagrange, they're the Lagrange multipliers. So I need to see. We will use. So have we used alpha? We use alpha for angular acceleration. Let's use beta at some point. Or maybe I'll just make the distinction that when we talk about Lagrange multipliers, those are the multipliers themselves. Okay. All right. Any questions so far, please? We need to now exercise this idea for a set of equilibrium points that we choose. Okay? All right, let's take the first set of equilibrium points and let me draw the figure. So let me select theta is equal to, theta 1 star is equal to 0. Theta 2 star is equal to 0. And we want to see if this equilibrium point is stable or not. What does that mean? I'll draw the hoop. Okay. If theta is equal to 0, then the bead is sitting right on the top of the hoop. Okay. It's sitting right here. The nice thing about this situation is if it is sitting there, there is no component of the gravity force along the tangential direction. So this is the tangential direction. There is no component of the gravity force there. There is, at that particular location, there is no component of the centrifugal force as well in that direction. And so when the bead is sitting there, it is completely in equilibrium. But the moment the bead is disturbed from that particular position, you end up with a situation that looks like this. And in a situation that looks like this, you see that the centrifugal force, which is pointing along the E theta direction, and the component of the gravity force that's pointing along the E theta, they're not cancelling each other off. Right? They're not equal to each other. And so the bead is not going to be in equilibrium if it is sitting at this particular location and it's given a small perturbation. And let's see if that is physically also what the eigenvalues say. Does this make sense to everybody? Okay, sitting at the top, give it a gentle nudge, it's just going to move out. And it's going to move out because of the imbalance between the centrifugal force and the force due to gravity. Okay? So if we calculate the eigenvalues, and first of all, the Jacobian matrix, so F1 is just theta 2, F2 is sin theta 1 times d by r omega square cosine theta 1. If I calculate the Jacobian, df1 by d theta 1 is 0 because f1 is not a function of theta 1. df1 by d theta 2, which is the second entry in the first row, is equal to 1. By the same token, df2 by d theta 2 is 0 because f2 is a function only of theta 1. So d theta 1 is, which is going to be done using the product rule. So I have sine theta 1 differentiated, so this is sine theta 1 times d by r, differentiated is cosine theta 1, plus omega square cosine theta 1, and then differentiation of cosine theta 1, which is going to be minus omega square sine theta 1 times sine theta. That's my differentiation, makes sense to you. Okay, first differentiation of sine theta, and then everything inside the bracket as it is. The second differentiation is I keep the sine theta 1 the same, differentiate things in the bracket for F2, which is just minus omega square sine theta 1. Okay? And this has to be evaluated at some theta 1 star, theta 2 star. Take a look at this quantity here. It's sine square theta 1, and then I have cosine square theta 1, and recall somewhere here that cosine 2 theta is minus sine square theta. Cosine square theta minus sine square theta is cosine 2 theta, the 2 theta angle. So this is going to be g by r cosine theta 1, cosine theta 1, cosine theta 1, cosine square theta 1, sine square theta 1, omega square is a common factor. So this is plus omega square cosine 2 theta. This is going to be your Jacobian matrix, and I'm going to write it down here and say so J is 0 d by r cosine theta 1 omega square cosine 2 theta 1 I'm assuming all of you know how to take eigenvalues. Yes? Wait some time. So for any matrix, square matrix, of course, so to find the eigenvalues, essentially here is what I do. I take determinant of j minus that's how one will find the eigenvalues. So I is the unit, the identity matrix. Lambda is a set of eigenvalues. So if I do that, I have determinant I is 1, 0, 0 and 1, so if I subtract that from j, this is what I'm going to end up getting. So this is going to be minus lambda 1 g by r cosine theta 1 plus omega square cosine 2 theta 1 minus lambda. Determinant of that matrix is 0. I is the identity matrix, lambda is some constant. And finding determinants, I just multiply the two lambdas and then subtract it from the multiplication of 1 and g cosine theta 1 and cosine 2 theta 1. Okay? So if I do that, I get minus lambda times minus lambda minus 1 times g by r cosine theta 1 omega square 2 theta 1 is equal to 0. and this has to be evaluated at the equilibrium point. Okay, so please be careful. So this is at some generic theta 1 star and theta 2 star. So if I write in general, the eigenvalues are going to be the following. In general, for some theta 1 star and theta 2 star, I'm going to have lambda times lambda, lambda square, the negative sign vanishes. Lambda square is equal to G by R cosine theta 1 star plus omega square 2 theta. Does everything make sense so far? Basic linear algebra here. Beyond that, the main idea is I need to evaluate these eigenvalues at theta 1 star and theta 2 star. So let's choose the first case. Be at the top of the hoop. So theta 1 star is 0. Theta 2 star is 0. If you included the presence of friction, then I would have this as a function of theta 2 star as well. Okay, because a component of theta dot will be present there in terms of friction. So we did not include it, so it's not the case situation for us. Okay, but typically when you study stability, you study it in the absence of friction. You just want to see inherently how bad or how good the system is about certain resting points. Okay, at theta 1 star, lambda square, cosine of 0 is 1, so this is G by R. Cosine of 2 times 0 is also cosine of 0, which is 1, so this is plus omega square. And which invariably tells me that lambda is plus or minus square root of the positive quantity. So this tells me one of the lambdas is greater than 0. And if that is the case, this perturbation that you give about this equilibrium position is going to grow with time, and the bead is going to just move away from that position. It is never going to come back there. It is possible that you give it a very large velocity. The bead is sitting there and I give it a very large initial velocity, the bead will just go travel and then at some point it will come back here, but it's not coming back to the same position. It has made an angle of pi rotations. So it's one rotation, right? So that's not the same equilibrium point again. So please be careful there. So this is an unstable equilibrium. So theta 1 star is equal to 0 is unstable. Theta 2 star is equal to 0 as well, both of this. And this is because any perturbation given about that equilibrium point will just grow with time. Does this make sense to everybody? Do you want me to write down these details, or this is sufficient to understand what's going on? Okay? Alright. Now let's take a look at the next case. Bead at the bottom of the hoop. And by the way, this kind of an equilibrium position, bead sitting on the top of the hoop, this is called as a hill equilibrium, because it is essentially like sitting at the top of a hill. If somebody pushes you, you're done for. You're not going to come back. Okay? This is the hill equilibrium. And this is a fully unstable position. beat at the bottom of the hoop, what do you guys think is going to happen? Is it going to be a stable or an unstable equilibrium point? Stable? All of you are fine with that? Really simple. Okay, so the thing that I need is just that, I'm going to write that down here. So the general eigenvalues are lambda square is d by r, theta 1 star, omega square, cosine 2 theta 1 star. So when the bit is at the bottom of the hoop, theta 1 star is pi. Theta 2 star is 0. So cosine of theta 1 star, which means cosine of pi, is minus 1. Right? So this is minus g by r. And then cosine of 2 times pi is cosine 2 pi, which is an even function. So this is omega square only, omega square times 1. So this is lambda square. Or if I write it, this is omega square minus g by r. What can you tell about the nature of lambda 1 and lambda 2? So if I say lambda 1, lambda 2 is plus or minus square root of, is this going to be a positive quantity? Yes.
Omega square is greater than g over r.
If omega square is greater than g over r, this is positive. If omega square is less than g over r, this is negative. Square root of a negative number is an imaginary quantity. So the solution, if omega square is less than g by r, is uniformly stable. That is, if I just give it a gentle nudge, in the absence of friction, it will just keep going back and forth. It is now going to settle down to the location of the beat at the initial point. But the perturbation is not going to grow with time. Okay? So let me write it out. There are two things happening now. This is a more complicated equilibrium position, as you can see. So for omega square less than g by r, this family of equilibrium points, theta 1 star, which is at pi, theta 2 star, which is 0, is steady. But if omega square is greater than or equal to g by r, typically greater than g by r, so at equal to g by r, this is the critical point, typically where something called as a bifurcation occurs. So at this point, the eigenvalues, at least one of them will become positive, and so the system is unstable. Am I making sense to everybody? So it's not a cut and dry case. Depends on the value of omega. If omega square is less than this quantity, this is a negative number, and so the system is uniformly stable. It just keeps going back and forth about that position, so the perturbation is not going to grow with time. But if omega square is larger than this quantity, then something funny starts happening. At least one of the eigenvalues has a real part, which is positive, and so the system is going to be unstable. The perturbation is going to grow over time. What happens is that when omega square is greater than g by r, the second family of equilibrium points kick in. You see, there are two families of equilibrium points, right? Theta 1 star is plus or minus n pi, and then the other one, I'll just write it out. So first family was for all omega square, plus or minus n pi, it's kind of understood. Then for omega square greater than G by R, we have greater than or equal to G by R, we have theta 1 star is plus or minus cosine inverse of minus G R omega square. So if you are sitting at the bottom of the hoop for low speeds of rotation, that position is a stable equilibrium position. But for higher speeds of rotation, that position becomes unstable. But then immediately, as soon as the bead starts traveling away from that particular location in the perturbation, the second family of equilibrium points kick in, and we have to see whether these are stable or unstable. Okay, so let's do that. So in this case, I can just write cosine theta 1 star is minus G by R omega square. Okay, and we may need to do some manipulations for cosine 2 theta and so on, but we'll do that. So lambda square is G by R cosine theta 1 and omega square cosine 2 theta 1 star. I'm going to recall another cosine 2 theta formula, which is 2 cos square theta 1 star minus 1. This is another cosine 2 theta formula. Okay, so cosine 2 theta So let me do the substitutions. Instead of cosine theta 1 star, I have the following. So lambda square is G by R, and then minus G by R omega square, because cosine theta 1 star is minus G by R omega square, plus omega square times 2 cosine square of theta 1 star, so that's going to be G square by R square omega square whole, and this is R equal 4, R square by omega equal 4 minus omega square. Let's do some simplifications. So this is lambda square is, so the first one becomes minus G square by R square omega square. Then I have 2 omega square, I have omega to the power 4 in the denominator, so this becomes plus 2 G square R square omega square minus omega square. Does this make sense to everybody? 2 minus 1 is 1. So this is G square by R square omega square minus omega square. And mind you, omega square is greater than G by R. If omega square is equal to G by R, this whole thing will become 0. But if omega square is greater than G by R, what's going to happen is that this denominator will become much more heavier, so that this term is going to be more dominant than the first term. So that this entire thing is going to become a negative quantity. And if it becomes a negative quantity, that's a stable equilibrium, because it's just going to oscillate about that particular location. Okay? So this is going to be always less than 0. And so this is a stable equilibrium position. by r omega square is a stable equilibrium point. Does this make sense to everybody? And once again, the reason for these things is the balance or the competition between the centrifugal force and the force due to gravity for a non-inertial observer who's sitting in the beam. Okay? At all these locations, your theta 1 double dot is 0, which means that for all of these values for which I satisfy the constraint that g by r omega square should be less than 1, my acceleration is 0, so those are all a family of fixed points. And if I plot it, you see here's what you see. So I'm plotting theta on the y-axis. So this is theta, or theta variation. Okay. This is let's say theta is equal to pi. Theta is equal to 3 pi by 2. Minus 3 pi by 2, okay, these are bounds, and then this is the parameter omega square. For omega square values less than g by r, so I'm going to mark something here, so this is omega square is equal to g by r. For omega square less than g by r, then all this entire branch, when the particle is sitting there, he is going to be in equilibrium, and this is a stable equilibrium. So what this means is, if the particle is sitting at pi, if the speed is less than g by r, if the speed square is less than g by r, any perturbation about that position is going to result in the particle behaving in a stable manner. The perturbations are not going to grow with time. Right after my omega square becomes more than g by r, this line becomes unstable. Which means that if the particle or the bead were sitting at the location pi, and if my speed omega square is greater than g by r, then that denotes an unstable equilibrium position. Okay? But then immediately, as soon as I cross over, I see that there are two new families of equilibrium points coming in. Two new families because this is plus or minus. And what will happen is that if I plot that cosine inverse of minus g by r omega square, that will just grow in the following manner, asymptotically reaching there, asymptotically reaching there, and these are going to be stable. Both these regions are stable, and this is just plus cosine inverse minus g by r omega square, and this is minus cosine inverse minus g by r omega square. Once again, what is being plotted here is the following. Okay? On the x-axis I have omega square. That's the speed. On the y-axis I have the equilibrium points. When I am sitting at an equilibrium point pi, when the bead is sitting at the bottom of the hoop, if my speed of rotation omega square is less than g by r, so if I am within this region here, that location is considered to be a stable equilibrium point, because any simple nudge from that location, that perturbation is not going to grow over time. But immediately, as soon as my speed increases beyond this critical speed, if my bead were still sitting at the location pi, then what happens is that it becomes an unstable location, and so the bead will have to start moving out because the perturbation is going to grow. But the great news is that the perturbation doesn't grow too far, and the bead will probably come and sit on the next family of stable equilibria. Okay, so if you take the hoop by a bead, and then you take it and maybe by a set of bearings as well, you rotate it very fast, put the bead on the bottom of the hoop, you bead after a certain speed has been passed, the bead will try to fly up, similar to the principle of a governor, James Watt's governor. The bead will fly up so that the bottom position is no longer stable, but it will latch on to another position that is completely stable, and it will just keep swinging there. Okay? And such a bifurcation, this is called as a bifurcation diagram. Bifurcation plot. We are plotting the behavior of the equilibria as a function of some parameter of the problem. This is the critical parameter, and this is because it looks like a pitchfork, it's called as a pitchfork bifurcation. Right? So this is a pitchfork, actually called a supercritical pitchfork bifurcation. This is a good type of bifurcation where a family of unstable equilibrium points will make the behavior of the system stable as the parameter is increased. So as my omega square increases, I go from an unstable to a stable behavior. The reverse of this is the subcritical pitchfork, where I start off with unstable behavior here. This entire line is stable, but the other two will be unstable. So I'll go from a stable location to an unstable location. Okay, and in many problems, it is important to tune your parameter. So that's called as a parameter that can be tuned. Typically, when you're looking at cantilever tips on atomic force microscopes, they undergo characteristics of resonance as they start scratching the surface, and you've got to tune them so that their behavior is stable. The behavior of the dynamical system is stable. Okay. So that's it for this particular problem. Any questions? Including the gentleman who's fallen to sleep. Not much sleep last night? No? I see that typically students are very tired these days. End of the semester. Yeah, it's a rough time. Alright, any questions please on this? And for your second exam, which is going to be sometime during the month of April, I'm going to have a stability kind of a problem in there, so that you make use of these ideas to tackle that. Okay? Yes?
Can those stability branches branch off into even more?
Yeah, there will be more of these types above and below. So I'm just drawing one between pi and 3 pi by 2 and minus 3 pi by 2. That is the minus pi, 3 pi by 2 and pi by 2 comes from, if my value of omega is very, very large, then this will become plus or minus 270 degrees. But if I start off by saying, okay, I have gone through 2 rotations, then I'm going to be sitting at 2 pi, and then I'll be going into 2 times 3 pi by 2, 5 pi by 2, and minus 5 pi by 2. This behavior continues down. Okay. So what I'm going to do next is we're going to move to rigid bodies. And I want to derive the kinetic energy of a rigid body. Okay? And once we do this, then we have pretty much all the elements to start tackling bigger problems. So kinetic energy. Of a rigid body. I'm sure most of you know that kinetic energy of a rigid body has 2 parts, the translational kinetic energy and the rotational kinetic energy. You may have seen that for a 2-dimensional problem, but for a 3-dimensional problem it's a much more scarier looking creature. Right? So we will look at it carefully. I have an arbitrary rigid body, center of mass is C. This little I is the location of the ith particle on the rigid body. We are essentially thinking of the rigid body as a collection of particles. This is the collection of particles. I is equal to 1, 2, n, C. C is the centroid or the center of mass. Center of mass definition from basic mechanics is the mass weighted average of the center of mass of the individual particles. Okay. Mass weighted average of the locations of the individual particles. Alright, so here I have a fixed Cartesian frame. I have J hat, K hat. I'm going to say that the rigid body is rotating at some rate omega. About its center of mass. Then I'm going to set up a rotating frame on the rigid body. Just to make sure that these directions are not coincident, I draw it slightly different. So dx, dy, dz. Okay, this is a fixed observer law. I'm going to draw some position vectors. Right, particle location, center of mass, point O, the same coordinate frame that I've shown there. There are three position vectors. One is the location of the center of mass as seen by an inertial observer. So this is an inertial observer. This is C/O. We're going to drop the subscript of O because we typically don't use it when you refer to an inertial observer. Then I have Ri/O is this line. Is the location of the ith particle as seen by an inertial observer at O. And then I have Ri/C, which is the relative position of the ith particle with respect to the center of mass. Okay. Perhaps just to complete everything, I can add the frame and so on. Why the definition of center of mass? And I'm not going to prove this, we will just take it and I'll work on this as RC. This is Ri. Okay, so by the definition of center of mass, the position of the center of mass is M1, R1, M2, R2. Does this make sense to everybody? You would have seen this for centroids of areas and so on. Okay. This is for the center of mass, or I can write this succinctly as RC is summation Mi Ri. I goes from 1 to n, the number of particles, divided by the total mass of the system. Summation I is equal to 1 to n Mi, which is with your permission, I'm going to stop writing this I is equal to 1 to n. Okay, it's kind of understood. Now I'm going to use the idea of vector addition, and we will just write down Ri, which is the location of the ith particle as seen by an inertial observer. This is Rc. So R I/C. Does this make sense to everybody? It's basic vector addition. I'm going to multiply both sides by Mi. And I'm going to take the sum of all of these things. Okay, so this is summation. So if I do that, I'm going to get summation Mi Ri is equal to summation Mi C summation Mi Ri/C. Okay, first I took mass Mi, multiplied it through both the sides, then I take the summation for each of these things. I do it for n number of masses, and I take the sum of all of these. Watch this. This is Rc is equal to this summation divided by the total mass m, or I can write m times Rc is equal to summation Mi R. This is from the definition of the center of mass. This makes sense to everybody. Just cross multiplying things. If I do that, and if I use that idea here, this quantity is essentially Rc times summation of all the Mi. So there is no I index on the center of mass location, so the summation is going to be only over the masses, and that's just going to give me the net mass of the system. Okay, so this quantity is just m times Rc, that is summation Mi Ri/C, which is equal to summation Mi Ri. Do you see something that I see here? Look at the boxed equation, look at the equation that I've written here. What is the conclusion you can draw from that? Yes.
It's 0.
Which is 0?
The summation of the masses times all the Ri/Cs.
Absolutely. Absolutely. This will cancel out with that. This is completely an algebraic result. Okay? There's no physical meaning attached to it. It's mathematical. It is just as a consequence of the definition of the center of mass. So first things we want to write, and we want to collect all these results, is that m times Rc is summation Mi. Alright. The second result is summation Mi Ri/C is 0. Which means if I take this expression and I differentiate it, and my mass is constant all the time, summation of Mi R dot Ic is also 0. I shouldn't have erased this figure, but with your permission. Okay. All right. So these are results that I'm going to collect here, and then eventually use. And I'm going to revisit this vector law of displacement that we just, vector triangle law that we just wrote. So Ri, don't need to write it, I slash C. I want to find the velocity of the ith particle, or certainly. That's going to be d by dt of Ri as seen from a fixed observer. So this is frame F1, this is frame F2. So this is the rate of change of the position vector as seen by a fixed observer. This is going to be the rate of change of the position of the center of mass as seen by a fixed observer. Plus the rate of change of this guy as seen by fixed. The first quantity on the left hand side, I'm going to call it as a V suffix, a VI, which is the absolute velocity of the ith particle. This is the absolute velocity of the center of mass, and then I have the last term. So VI is equal to VC plus, now what's this? RIC is a relative vector, relative position. I'm going to take that, it's written with respect to frame F1. I'm going to do the following. I'm going to say this is d by dt of RIC with respect to frame F2, and then omega of the frame F2 with respect to F1 crossed with RIC. All I'm doing is this rate of change of a vector equation that we have seen in the past. Okay? What is this quantity? I'm sitting on the rotating frame. I'm looking at the distance from point I to point C and taking the time derivative of it. It has to be?
Yes, it's going to be 0. It's a rigid body.
Does this make sense to everybody? The distance between, by the definition of a rigid body, the distance between 2 points on the rigid body is fixed. So if I'm sitting on the rotating frame, that distance is not going to change. Okay? But if I'm sitting in an inertial frame and looking at that distance, even though it will not change in size, it will not change in magnitude, that is still a vector that is rotating, and so the rotation of that quantity is what you are seeing here as the omega cross r. Okay? And so we have this equation, VI is VC, and omega, I'm just going to call this as omega of the body, with your permission. Crossed down IC. This is the angular velocity of the body with respect to an inertial frame. And this is the third equation I'm going to use in my grouping here. So we say is VI omega V cross or and one more thing I forgot to do it here, but RIC, I'm going to write its components as some x I hat, y j hat, z k hat. Okay, does this make sense to everybody? Some arbitrary vector, okay, x I hat, y hat, and z hat, k hat, and then omega of the body is some omega x, omega y, omega z. And there is absolutely no necessity that I should use I hat, j hat, k hat. I can as well write the components of R I slash c using the EX, EY, and EZ frame. No harm done. I can choose anything that I want to do. Right? Within certain limits. Alright, so far so good. Now I'm going to introduce you to a new way of doing cross products, because I'm going to use it for this particular problem. Maybe some of you know this before, but if I take a vector A, from AX, AY, AZ, vector B is how do you do cross products? You take the determinant, you write the first row with the unit vectors and second row with the A element and the third row with the B element, right? So A cross B is A hat, A hat, A hat, AX, AY, AZ, BX, BY, BZ. You evaluate this determinant. This is a typical old-fashioned way of doing things. Now I'm going to say that this is also equivalent to the following. A cross B, and then before that some notational changes. This represents the vector A written in the column form. So this is AX, AY, AZ, B, X, B1, B. So this is just a 3 by 1 column vector, 3 dimensions. And I'm going to say that the cross product of these two vectors is now S of A, hang on, I'll define what S of A is, times B transpose. So S of A is going to be a 3 by 3 matrix. This is just B, I'm sorry. And this is 3 by 1, and the product of a 3 by 3 matrix and a 3 by 1 column vector gives me a 3 by 1 column, which is typically what your determinant also gives you. This is going to give you a vector, right? Cross product of two vectors is a vector. What is this S of A? S of A is called a skew symmetric matrix. So S of A is defined in the following. All its diagonal elements are 0. In the first row, you're going to have the elements only for y and z written but in the positions offset. So this is minus az and then ay. Okay, this is just another way of doing things. Then I said, okay, this is going to be a skew symmetric matrix, so the off diagonal element minus az is going to be replaced by az in the next row. And here, I'm going to have minus ax. And the last row, if you return the first two, is easy. This is minus ay, and this is ax. So once again, the diagonal elements are all 0. In the first row, in the y position, I write the negative of the z, and then in the z position I write the y value of the component of the vector A, and they are all skew symmetric, which means that the off diagonal should be of the opposite sign as the element above the diagonal, and likewise minus ay plus ay, ax and minus ax. And every row should contain only one negative sign. Okay, these are like rules of the game. Essentially, I am setting up a game. These are the rules of the game. If you write S of A this way, then A cross with B is going to be 0 minus AZ, AY, multiplied with Bx, By Bz, and this is going to give you the cross product. You can compare it and then find out that it gives you the same answer as that. We're not going to do it. And a couple of things. So S is skew symmetric. Means that the transpose of S is negative. Okay, so S transpose is minus S of A, and you can as easily verify it and see. So keeping all that in mind, this is just to make things a little more simpler, even though this is like a new thing. Maybe some of you have come across this before. This is my latest result. So I want to sneak it in somewhere here. So any cross product is S of A times B. Okay? What's my aim? My aim is to obtain an expression for the kinetic energy of the rigid body. So let's do that. So start off with the kinetic energy of the ith particle. So this is half mi Ri dotted it. Ri dot is nothing but Vi. Okay. So this is half mi. This is the expression for the kinetic energy of the ith particle. With your permission, I'm going to substitute for this has to be flipped. Nobody said anything. This is Vi. This is Vc. So I have to substitute that. This is half mi Vc omega b crossed with Ri slash c. You see why we are doing the cross product that way is because there is a cross product here. And so I want to apply that idea onto this cross product so that things become slightly more simpler, depending on how we look at it, of course. This is Vc. Half mi times this entire stuff. This is just a dot product of two vectors. So I can take each one of these elements and then take the dot product with the other. So this is Vc dotted with Vc, Vc dotted with omega b cross r I slash c, and so on and so forth. Okay, so if I do that, or if you want, you can write this to begin with. You can write this as the following: or dot I slash c, just to make it a little more easier to write that. It's the same thing, no difference. Expand this, and do this only once. Half mi Vc dotted with Vc. Dot product is commutative. Okay, so VC dotted with R dot I slash C is the same as R dot I slash C dotted with VC. So I'm collecting two of these. There's a factor of a half, so that becomes 1. Plus MI VC dotted with R I slash C, then half MI R dot I slash C crossed with R dot I slash C. And I'm going to take the sum of all of these so that I get the total kinetic energy of the body, right? So T is summation Ti. I goes from 1 to n. I'm not going to write the summation. When I write the summation, watch how I write it. With your permission, I'm going to skip some things. First term. If I am summing over all the I indices, the mass is the only thing that undergoes a summation because this is not dependent on any I index, and so this is just going to be summation of all the masses, I masses, that's the total mass of the system. VC dotted with VC is VC squared. Okay, so this is going to be half M VC squared. So this is a term that you've always seen before, right? Then I'm going to have summation, and look at this. This term, I'm going to write it as VC dotted with MI R dot I slash C. There is nothing wrong with that. I'm just shifting the order of doing the things within the dot product. The mass is a constant. It's not a vector, right? It's a scalar quantity. So I can take this and I can attach it with that guy. Okay? And so I'm taking the summation of all of that over Vx I VC dotted with MI or dot I slash C. We're almost there. We'll continue on Thursday. Plus half summation I is equal to 1 to n